let's look at radioactive decay. Now, the mental image you should have is of a material with loads of undecayed radioactive nuclei, something like plutonium, that can decay into uranium. And we're going to watch this sample of material, and as time goes by, some of these nuclei are going to decay, and they're going to decay into a different material. And so as we watch it, gradually, more and more of them change from plutonium to uranium. And we want to describe this mathematically. And the key insight here is that if we have some number of particles n, so in this case n started off as 18, the number of undecayed nuclei decreases with time, but it doesn't decrease like this. It doesn't just go to 0 after a fixed amount of time. Instead, it just gradually drops down. And if you have a very large sample of atoms, as you normally do, this line actually never reaches the time axis. It never goes to 0. It just gets smaller and smaller and smaller. If you do this experiment with 18 atoms, then it will eventually hit hit 0, but to all intents and purposes, in reality, it never does. So I want a differential equation that describes this. So I'm going to focus on the gradient of this graph. I'm going to focus on the gradient, and I'm going to say that this gradient, it's a bit messy, this gradient is dependent only on the number of particles I have. So I'm going to say that dn by dt is proportional to the number of particles I have. But just to be careful, remember that it's proportional to the negative of the number of particles I have, because it's sloping downwards. And as we all know, I can change that into an equation. dn by dt equals minus kn. And it's traditional to use the letter lambda rather than k. So I'm going to replace that. And this is our differential equation, and we're now just going to go ahead and solve it. So I'm going to bring this n over to this side, 1 over n dn dt equals minus lambda. And now we integrate dt. I'm going to switch colors just to make it clear what I'm doing here. And we can play this neat trick where the dt's cancel. And so we have an integral 1 over n dn, and you need to remember that that is the natural log of n, equals, and on the right hand side, minus lambda is just a constant, so integrating dt, you just end up with minus lambda t. Now, I want to get rid of this natural log. It's not very convenient to have that there, so I'm going to raise both sides to the power e. I'm going to have e to the power ln n equals e to the power minus lambda t. Now, I'm forgetting one thing. Remember, when we integrate, we have constants. They always integrate, and we have plus a constant. Plus a constant. Right now, I'm just going to subtract c1 from both sides to bring it over here. So that's going to look like this. Ln n equals minus lambda t plus c2 minus c1. And I'm just going to call this thing c, just to keep my algebra a little neater. Ln n equals minus lambda t plus c. And now we raise everything to the power e. E to the ln n equals e to all of that. And e to the ln n, this cancels out. So we have just n equals. And if you remember your rules for handling exponentials, this is the same thing as e to the minus lambda t, e to the power c. Now this thing is just a constant, and it's actually the number of particles that we started with. So I'm just going to call this n naught. So we have n equals n naught e to the minus lambda t. And this is our equation describing this curve that we had right at the start, n versus t. N equals n naught e to the minus lambda t.